Okay, so good afternoon. I'm Liu Shangxi. So now I'm presenting my project, which is an advanced synchronization to resolve the dining philosophy problem. So first, let me introduce my scenario. So we have five threads that representing the philosophers and five binary semaphores that representing the chopstick. So the core function for these threads is to alternate between the thinking and the eating. The primary challenges is to coordinate these traits to prevent the system-wide stalls when they all compete for the same resources simultaneously. So let's see the problem which how the symmetric code really fails. So we define the symmetric problem logic. So in this system, every thread follows the same exact rule to pick up their left chopstick first, then the right. So while this seems logical, but it actually creates a fatal dependency in a concurrent system. This is because that Ubuntu scheduler manage these threads simultaneously, and it is actually highly likely that every philosopher will grab their first resources before anyone can grab their second. So let's see for our code. So this is the complete source code, which this we can see the implementation of this flow. Within the philosopher function, each thread is execute the same wait. We can see the same wait command. So it's like this one. So uh on the index ID. So which this is actually represent the left chopstick. Following, this is a US sleep command. So will be this one. So this is actually delay can cause the delay is critical, which is actually stimulates a context switch window in the Ubuntu. So to ensuring that all the threads have enough time to pick up their first fork before any thread can attempt to grab the second. So without a specialized condition to break this sequence, the code effectively forces the system into a state where all resources are held and all the threads are blocked, and to satisfying the theoretical requirement for deadlock. So let's see what's the output for this one. So this is actually basically how we run the code, insert our code and then run it, compile, and this is how it's run. So this is actually our output. So looking at the output, so uh, here's the actually this is actually terminal output from that stimulation. So it perfectly mirrors our code analysis, and this is we can see that the philosopher 0 through 4 is actually successfully pick up the left and then waiting for the right. At these 5 specific lines, the terminal stopped completely, and this happened because the same wait command, the function, has decrement all the 5 semaphores to the 0. So every thread is now calling the same wait command on the semaphore that is already 0. So the Ubuntu kernel plus puts all the 5 threads into the permanent sleep state. So this program has not crashed, but is trapped in the circular wait where no progress is actually possible. So how to solve this? So I will implement a symmetric rule, which this is a creative approach that breaks the circular wait condition. While philosophers 0 through 3 pick up the left, then right. So the final thread is programmed to pick up the right chopstick first. This is to ensure that the first and last philosophers are actually competing for the same physical chopstick as their very first move. This is to prevent a closed loop of dependency. So now this is our code that is provide the solution. So the brilliant fix is found in the conditional if. You can see that id is equal to n minus 1. So we can see it here. So for the last philosopher, we reserve the argument that we call the same wait command or the neighbor index for the current index before the current index. This is to create a resource hierarchy by changing the acquisition order for just one trade. We will guarantee that at least one chopstick will always remain on the table. So one philosopher will be blocked at their first fork, which allow their neighbor to pick up the same fork as their second resources to complete their meal and release for both forks. This is to ensure the system maintains aliveness and continues to process trades even under heavy load. So now let us see the output. So this will be the output for our solution, which actually is evident. So unlike the frozen log, this is actually output is active and scrolling. So you can see the philosopher actually successful entering the eating state, and note that the meal count 1/3, 2/3, and 3/3. So this is actually showing that the trade is completing its full life cycle. Because the code now actually allow the philosophers to put their chopstick after eating by the same pause command. So the resources are cycled back into the pool. So the final line, the success all the philosophers have eaten, prove that the asymmetric code logic has entirely bypassed the deadlock trap that we saw it earlier. Okay, now so we can see the comparison. So this comparison table is actually summarize our finding, which the deadlock demo is actually the thread were permanently blocked and the CPU and set idle. So in contrast, our synchronized demo shows that the dynamic thread status and active task completion. This contrast proves that the asymmetric implementation is a superior and more robust method for managing high concurrency resources on Ubuntu. So last but not least, our project demonstrates that synchronization is about strategic ordering, not just locking. So my implementation successful to resolve the circular weight and ensuring system integrity. So this proves that by targeting the theoretical cause of the problem, we can create efficient multi-thread applications. So that's all for my part. Thank you. Okay, so as I finish my presentation, and this is actually my proof that I done in the Ubuntu. And so this one is how I started to link my directory and my code inside for this one, and I compile the code and run it. So this is the output, and same for this one is the after.c is actually the solution that I solved the problem. So and this one is the output for it. So that's all for my overall presentation. Thank you.